Good morning to you all, or good afternoon. Hope you are doing well once again. We are going to go ahead and start the next unit, which is going to be one section in chapter 14 of that IB book, and then the rest of them are going to be in chapter 15. I am going to create some Schoology assignments for you to do. It's probability, getting into probability here, things that are on the IB exam. And so I want to make sure that I can kind of see how you guys are doing to make sure you're understanding. This first section is on 14.3, which reviews some of the stuff we did last year in AS Algebra 2 with the counting principle, combinations, and permutations. And so this is just prior knowledge that we need before we get into chapter 15 with the probability. So today, this part is not probability. But I will tell you that some students do find this to be the hardest section. So I would strongly encourage you to make sure that you come in sometime during my office hours or some other time, email me and we'll find another time, and you ask me some questions on this if you're getting stuck on some of the homework problems that you have. As we get into this, you can see our objective here is to understand how and when to use this multiplication counting principle, a combination or permutation in these word problems. And then moving forward, and we're doing it with probability, just realize that not every problem is a permutation or a combination. And so I'm going to be talking about this blank method that you would have seen back in Algebra 2 as well. Now, to kind of get started, in your IB packet, you actually have many of the formulas, if not all of the formulas that we're going to talk about in this unit. So it might be a good idea to find that IB packet that I gave you with all the formulas. I will tell you that a lot of the formulas are no longer required for IB. I shouldn't say a lot of them. Some of them are no longer required for IB. For instance, today when we talk about permutations and combinations, so you might recall it was n permutations of r. And so that formula was n factorial divided by n minus r quantity factorial. So you did learn that formula last year. You had to do some stuff by hand with that, okay? And then your combination formula, n combinations of r, was n factorial over n minus r factorial. So the same thing as we started with permutations, but then it was also times r factorial. And this last r factorial is talking about repetition of things when order doesn't matter. Remember that permutations are when order matters. So you're giving specific places or lining things up, giving specific positions, and then combinations are when order doesn't matter. So that last r factorial is dividing out the repetition basically, and you're going to see us do some of that. So as we move through, again, these two formulas are not required for IB. There are other formulas that you see in your packet that you're going to have to know, but you would just use your calculator. So on your graphing calculator, I can pull mine up real quick, but on this graphing calculator, you're just going to type in, let's say we're doing 5 combinations of 3. You would do 5 and then math. You would go over to probability, and then number 3 is combination. So 5 combinations of 3 would give you 10. If it was 5 permutations of 3, you should have more when order matters. So math, and then PRB, so 5 permutations of 3. There's 60. Again, because then you would be dividing out 3 factorial. Remember 3 factorial, you can go back to math. Factorial is that exclamation point. That means 3 times 2 times 1. So if I take 60 and divide it by 3 factorial, that 60 divided by 6 gives me the 10. Now, if you have just a scientific calculator, you can do these as well. So all you have to do is you have to look for the PRB button, or PROB. There's a probability button, and you're just going to underline it. I think might be on the second line. So we can definitely meet if you can't find it, and make sure we figure that out. So there are some good examples in the book. I think what I'm going to do is still scan the book, but we're just not going to be working out of it. You'll just work through Schoology. But there are some good examples, and I just want to talk a little bit about a couple of them. So let's say we have a couple extra examples really. So let's say we have a combo meal. We have 3 burger choices. We have 4 sides and 2 drinks. And if we're choosing a burger, a side, and a drink, how many meals are possible? This is where talking about how we can kind of use this blank method. This is not a permutation or a combination. We have burgers, we have sides, and we have drinks. And so sometimes I'll just kind of label underneath what it is I'm finding. And so it says we have 3 burger choices, we have 4 sides, and we have 2 drinks. And so it's called the fundamental counting principle or the multiplication counting principle, because then we're going to multiply those out. So we would have 24. So if we get to combinations or permutations, let's say we have 14 people in a class and we're choosing a 3-person committee. So if we're choosing a 3-person committee, this is just generally kind of selecting 3 people out of the 14. So in this case, order doesn't matter. So if order does not matter, that's a combination. So in this case, we would do 14 combinations of 3. Now I will tell you, the notation for IB is to kind of do like a column vector is what it looks like. So they will use this notation where they just stack it. So that would be 14 combinations of 3. I have also started seeing them where they do this, which is kind of a new notation as well, where they just kind of have it diagonally there. Okay, so again, you could type that into your calculator. I would encourage you to do so, whichever calculator you're using, or again, you can get the Chrome app if you want the graphing calculator. So that's listed in Schoology, and you would get 364. So for the next one, 14 people in a class, we're electing president, vice president, and treasurer. In this case, order does matter. Because if I pick student A to be president and student B to be vice president and student C to be treasurer, well, if I change it and make student B president, that's a different way to have these offices. So order matters. So this would be a combination. Sorry, this would be a permutation. That's what I was thinking, and then I said the wrong thing. So for 14 permutations of 3. And again, that's going to give you more options. So 2,184. So again, I would take a moment to type that in. You can pause anytime that you need to, but make sure you're typing those in. The other way you can think about this one is you can think about having 3 lines. So again, you don't always have to do a permutation or a combination for everything. Sometimes you do. But if you think about president, vice president, and treasurer, you would have 14 people that you could pick as the president. Then you would have 13 people to pick as the vice president, because you can't be in both of those roles. And then 12 people to pick as the treasurer. Okay, that's the same answer. Okay, that's the same as 14 permutations of 3, because it would be 14 factorial over 11 factorial. So again, sometimes using that blank method is helpful. So you can use that blank method when it's a permutation or when you're just talking about different categories, when order doesn't matter and you're just selecting them, you need to be using a combination. Okay, so let's look at some other examples. So again, I've given you the page in the book, so I will scan those in and just have that available. You can look back at more examples, but this would be page 500, number 1. So as we're doing these, I want you to visualize the situation. I think that will be helpful to you. So we have 5 different colored flags that are run up a mast. How many different signals can be produced if all 5 flags are used? So again, visualize what's going on. So again, I'm not an artist, but the idea is we have a flagpole here. And we're going to have these flags, these 5 different flags that are going up this flagpole. And so the question is, how many different ways can this happen? So if I just make them 5 different colors, that's obviously one way it can happen. So how many different signals am I able to produce? So you have to ask yourself, does order matter? That's one thing you can ask yourself. Or can I use the blanks at some point? And so order does matter. In this order, I have light blue, purple, red, green, blue. Okay, but think about how many options do I have for the top flag? Well, I have 5 options for the top flag. For the next flag, I would only have 4 because I only have 1 of every color. Then I would have 3, 2, and 1. I'm using all 5 of the flags. So that's one way you could do it. You would multiply those out and get 120. But you can also think that the order in which we have the flags is important. So that would be 5 permutations of 5. So the left number is the total you have to pick from. The right number is the number you're actually picking. So if it just said you had 5 flags and you wanted to know how many ways you could get 3 flags on the flagpole, that would be 5 permutations of 3. So that would also be 120. And it's also the same thing as 5 factorial, because 5 factorial is 5 times 4 times 3 times 2 times 1. It's all the integers down to 1. Okay. So the next one says, how many different signals can be produced if any number of flags is used? So I kind of alluded to this a moment ago, but that means we could use 5 flags, or we could use 4 flags, or 3, or 2, or 1. Now, could we use 0 flags? Well, no. If we don't use a flag, sometimes 0 is possible, but in this case, if we don't use a flag, then we're not going to have a symbol. Okay, or a signal, excuse me, because we're trying to produce signals here. So 5 flags, or 4 flags, or 3, or 2, or 1. So order still matters. So to figure out the number of ways to get 5 flags, we would have 5 permutations of 5. So we know that's 120. Or we could have 4 flags. The word or, as we're doing these, typically implies addition. Maybe you remember that from last year. So if I want to figure out how many ways could I get 4 flags to make a signal, again, we have 5 to choose from. Again, order still matters. It matters what color I'm putting on that, okay, to be a different signal. So we would have 5 permutations of 4. Okay, and you could type that into your calculator. I believe that also gives you 120. And then we would do or 3. So that would be 5 permutations of 3. And you guys, I think, are hopefully getting the idea here. And then 2 would be 5 permutations of 2, and then 5 permutations of 1. So we would find each of those and we would add them together. So 5 permutations of 3, getting 60. 5 permutations of 2 is 20. 5 permutations of 1 would be 5. So we would add those up and we would get 325 signals. Now, I know the last one, I didn't write signals out to 120. It is 120 signals. Okay, IB is not going to be really picky about you labeling. They never are. And on the Schoology assignment, I've tried to provide the labels for you. You won't type the labels in. So if I left a label off, then you're just going to type in the number. So that's how you would do when it says any number of flags used for that symbol. Okay, so the next one, this would be number 3, if you want to look back at that. But in how many different ways can 3 boys and 4 girls be seated in a row? So we have 3 boys and 4 girls, and we're trying to seat them in a row. So it's asking how many different arrangements basically can we have of these people when it says how many different ways, how many arrangements could they be seated in a row? So if we have 3 boys and 4 girls, we have 7 people. Now for this first one, it's just very general. We have seven chairs, and the question is how many different ways can they be seated in those 7 chairs? Well, we have 7 people that could be in the first chair. Okay, so as we're looking at this, it's not giving us anything specific. This first chair could be a boy or a girl. The second chair could be a boy or a girl, and so forth. So we have 6 people that could be second. Then we would only have 5 people, and 4, 3, 2, 1. And again, we're going to multiply because we want a boy or a girl, and then the next seat a boy or a girl, and the next seat a boy or a girl. So that word "and" is implying multiplication. So this would be the same thing as 7 factorial. This would also be the same thing as 7 permutations of 7. If you thought about it that way, any of those would be correct. So we would get 5,040 different ways for that to happen, because we can again have boy or girl for any of those. But then the next question gets a little more specific. It says, how many ways can this be done if no 2 girls are sitting next to each other? So again, I still have 7 people. So I have 4 girls and 3 boys, but I can't have any girls next to each other. So we have to think about how this would be. I have more girls than boys. So I could have a girl here, but I couldn't have a girl next. So I'd have to have a boy, and then I could have a girl and then a boy. So I'd have to go back and forth, girl, boy, girl, boy. And since I have 4 girls, Okay, if I started doing boy, girl, boy, girl, boy, girl, I'm out of boys. So then I'd have to do a girl at the end. So I couldn't do that. Okay, so I got to make sure that I don't have the girls sitting next to each other. So the question becomes, how many girls do I have to pick from? Okay, well, it says we have 4 girls. So I have 4 girls that could be in the first chair. And then if we think about the next girl, I would only have 3 girls that could be the next girl seated there. And then I would only have 2, and then I would have 1 at the end. So that would be girls because I have 4 of them. Then for boys, I would have only 3 boys that I could pick from to be in that first chair, and then 2 and then 1. And again, we're going to multiply each of these together. So you could multiply them out. That would give you 144. So there's 144 different ways. Okay, you might think about that as you see 4, 3, 2, 1 with the girls. So that would be 4 factorial for the girls. And then for the boys, you have 3, 2, 1. So that would be times 3 factorial. Okay, which is also 4 permutations of 4 times 3 permutations of 3. So again, different ways you can do them. So if you were thinking of any of those, that would be acceptable. The last one on this one says, what about if the ends are occupied by girls? So again, these blanks are going to help me kind of visualize. Again, I mentioned visualizing what's going on. So the ends have to be girls. So I'm going to go ahead and put girls here. And I don't know, anything could be for the rest of them. So these could be a boy or a girl, or all of these other ones. But I still have the stipulation that I have 3 boys and 4 girls. So if we start putting numbers to it, okay, I have 4 girls that could be this first chair, and I have 3 girls that I'd be able to select from to be the last chair. So remember, I have 7 people total, but I've already had to fill up 2 of those people. So I have a total of 5 boys or girls remaining. And it doesn't matter how I situate the rest of them. So that means I would have 5, 4, 3, 2, 1 for the middle chairs. Again, we're going to multiply all those together. So as we do that, we would get 1,440. Now, again, I'm putting commas. On Schoology, I've allowed for commas or no commas. As the numbers get really large, you should be using commas. Okay. So again, you could think of this as 4 times 3 times 5 factorial if you just recognize it. But I don't know that I would think that as I'm working the problem, but maybe as I'm typing it in, that might be a way that I would type it in, because I have a 4, a 3, and then I have 5, 4, 3, 2, 1. Okay, we're going to do another one here. It says, how many different arrangements of the letters in the word hippopotamus are there? So sometimes this will say, how many different distinguishable permutations do you have for the word hippopotamus? There's different ways you can see it. But as we look at the word hippopotamus, obviously the order matters, because if I put it in this order, I get hippopotamus. But if I start rearranging them, I'm not going to get the same word. The issue here is we have some repetition. So if we look at the letters on this, we recognize that we have multiple P's. So if I look at P's, we have 3 of them. And if I look at O's, we have 2 of them. So let me jump to something just a little simpler. If I had the word book, so let me start with that word, the word book. So if I had that and I want to know how many different ways I could arrange it, we obviously have 2 O's. So that's one way. But if I just switch the O's and I just put the subscript so you could see it, I really haven't spelled a different word. Okay, I could do this. I could also do where I have the second O and then the first O. And again, in the grand scheme of things, I'm putting the 1 and 2 on it for us to see it, but this one is no different than the first one, and this one is no different than the first one. And then we could continue going, okay? But what happens is, because of the ways that I'm rearranging the O's, okay, I have to start dividing those out. Okay, so as we're looking at this, if I had 3 O's, again, I could as I rearrange those, how many different ways can I rearrange 3 O's? How many different ways could I rearrange 4 O's? So we're going to end up dividing out that repetition. And there is a formula there on the bottom of page 496 if you want to look at it. But really what we're going to do is we're going to take the total number of letters, okay? And we're going to do it factorial. And then we're going to take it and divide it by the repetition. Whatever repeats factorial. And it might be that we have more than one thing repeat like we do in the word hippopotamus. So if we were doing this for book, again, the idea for the word book is if we were trying to figure out how many ways to arrange it, we would have 4 letters, 3 letters, 2 letters, and then 1 letter. So that would give us 24, but then I'd have to divide out the fact that those 2 O's don't matter. So that would be 2 factorial, which is 2. So it would only really give us 12. Okay, 2 factorial is 2 times 1. So this would really be 4 factorial divided by 2 factorial, which would definitely give us 12. Okay, so if we take that up here, we're going to take the total letters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we're going to have 12 factorial. And then we're going to divide it by whatever is repeating. So I have 3p, so 3 factorial, and then 2p, so 2 factorial. Now you cannot take 3 times 2 and get it 6. You can't take 12 divided by 3 and call it 4 and then divide by 2. That doesn't work. Okay, 12 factorial literally means 12 times 11 times 10 all the way down to times 1. Okay, 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. Okay, so you can't divide those out. So really you could just type it into your calculator. You would want to put the denominator in parentheses as you're doing it. So 12 factorial, again, under that math or that probability button, and then divide it by 3 factorial times 2 factorial. Or you might even say, okay, that's 12. So when you do that, you get 39,916,800 different ways that you could rearrange those letters in the word hippopotamus. Some of them make words, some of them do not. Okay, so there would be that many arrangements. Okay, so that kind of gets to some permutations and combinations and fundamental counting principle. Again, there are a couple on your homework that are not going to be just like these. Okay, if you remember from last year, not every single one is the same. And we really didn't do any combination examples here. I think we did one at the very beginning, but there are definitely going to be some combination problems on your homework, even though we didn't do anything specifically here. I don't remember off the top of my head how many there are, but definitely want to see that. Okay, so we're going to go on in this lesson just to 15.1 because it's going to be pretty simple here, talking about just basic probability. So that's kind of going to be the next section. So again, you'll have this page to reference if you want to, but I've really included the example down below, but there's just some things I want to highlight. The first thing I want to highlight is what's a sample space. Okay, so if it's asking you for a sample space in the homework, a sample space means to list all the possibilities. Now, an easy way to list all the possibilities is by showing a tree diagram. Now, sometimes the tree diagrams can get very large and we wouldn't want to do that. Okay, but sometimes they're not. So showing a tree diagram. So here it says 2 coins are tossed. Find the probability that 2 tails are showing or that a tail is showing. So this is where you may want to list out the sample space by a tree diagram. So we're going to toss 2 coins. On the first toss, we could get heads or tails. And then on the second toss, we can get the same thing, heads or tails, heads or tails. So this allows us to pick up our sample space by looking at the end. So we could get heads and then heads. We could get heads and then tails. We could get tails and then heads. We could get tails and then tails. So those are our 4 possibilities. And we see here, we have 4 possibilities by the end of our tree. But our sample space is when we have them listed out. So again, this is a very simple sample space, but it can help us figure out the probability. So what's the probability that 2 tails are showing? Well, that would be right here. So it would be 1 out of 4. What's the probability that just a tail is showing? Okay, so if we're looking for just a tail, okay, that means 1 tail, okay, not 2. So we have 1, 2. So we have 2 out of 4, which would be 1/2. So a tail would be singular there. So just trying to understand sample space and being able to list those out. The next thing we want to know, again, just a representation here, is what a lattice diagram is. So a lattice diagram, you guys did these, again, back in Algebra 2, but a lattice diagram is basically just another display. So we just looked at a tree diagram. Now we're looking at a lattice diagram. So it says find the probability of getting a sum of 7 on 2 throws of a dice. So in this case, we could kind of represent this by what they would call a lattice diagram. So the first time we roll the die, we could get the numbers 1 through 6. The second time we roll the die, we can get the numbers 1 through 6. And so then we're able to show the sums. Okay. This is a sum of 7. So a 1 and a 1 is a 2, a 1 and a 2 is a 3, and so forth. So we could create, and you should be able to create this lattice diagram. Now, as we look at this, if it wants the probability of getting a sum of 7, okay, we need to know how many total sums are possible. So we have a 6 by 6, so it's not 12, it's 6 by 6, which is 36. There's 36 numbers in that lattice diagram. So I want to recognize that. And so then if we want to know the probability of getting a sum, remember you have your sum, a sum of 7, you could use that notation. How many 7s do we have? So there are 6 7s out of 36, so we would have a 1 out of 6. So it's the number of 7s divided by the total number of sums that we have. So again, basically we're able to come up with this. We could come up with the sample space. So the sample space would be that we could get a 1 and a 6. We could get a 2 and a 5. We could get a 3 and a 4. We could get a 4 and a 3, a 4 on the first row, a 3 on the second, a 5 and a 2, or a 6 and a 1. So that would be our sample space. So again, the lattice diagram is just another way. I will mention back here on this sample space one, sometimes you'll see, they'll list out sample space like this, and you'll see books that will use the braces to show a sample space. Okay, IB's not picky about that, so if you do ever see that anytime, just know that that's just saying what are all the possibilities. Okay, it'd be a little hard to do this because I have commas, so I guess you could use semicolons between them and list them out that way. But the lattice diagram is more of a picture of what's going on. Okay, the last thing I want to discuss is going to be on page 507. It's number 13, and I'll let you know what it says. It says the die is thrown 3 times. I didn't type this one out. So a die is thrown 3 times. It wants to know the probability of part A getting 3 6s. So I'm actually going to use better notation than that even. So the probability of 3 6s. So that's the first one. So again, visualize what's going on. You throw a die 3 times. What's the probability of getting a 6 on the first throw? Well, you would have 1 6 out of 6 total. On the second throw, these are independent. So when I throw it again, I have a 1 out of 6 chance of getting a 6. And then on the third one, I have another 1 out of 6 chance of getting a 6. So if I multiply those out, we get 1 out of 216. On your homework, you are going to be using fractions. The second one says, what's the probability of getting 3 even numbers? Okay, so again, we're throwing it 3 times. I'm going to go ahead and just put my 3 lines there. So how many even numbers do we have? Well, on a die, we have 2, we have 4, and we have 6. So we have 3 out of 6. And then the next roll, we would have a 3 out of 6 chance and a 3 out of 6 chance. Or you might say 1/2 times 1/2 times 1/2. So this would be 27 over 216, which does reduce to 1/8. So again, answer should always be reduced. And then the last part here says, what's the probability of getting 2 odd numbers? Okay, so 2 odd numbers. Now remember, we're throwing a die 3 times. But it's saying 2 odd numbers, so that means we're only getting 2 odd numbers. So let's think about how we can get that. If we have 3 rolls, that means we could get an odd number, another odd number, and then an even number. We could get an odd, an even, and then an odd. Would be another choice that we have there. See if I can move that out of the way. And then the last choice is that we could get an even, an odd, or an odd. So those would really be our only choices. So I'm going to put the word or between them. Now remember that the word or means we could add. So let's think about the way that could happen. Okay, how can it happen that I get an odd, an even, and then an odd? Okay, well, how many ways can I get an odd? Well, there's 3 out of 6. Odds are 1, 3, and 5. So there's a 3 out of 6 chance there. So that's 1/2. The next one, I would still have a 1/2. And then I'd also have a 1/2 for the even, because it's the same chance to get odd or even. So that's 1 out of 8. Or for the next one, I would have the same probability, 1 out of 8. And then for the last one, we would have 1 out of 8. But I have 3 of them. So remember, the ors we typically are adding. So the idea is we're taking 1/8 plus 1/8 plus 1/8. Okay, because again, I'm taking the 1/2, 1/2, and 1/2. If we do that only, okay, that gives us the 1/8, but that's only one way that we could get 2 odds. So you have to take into account that there's 3 different ways that can happen. So our answer really is 3 over 8, because 1/8 plus 1/8 plus 1/8, okay, would be 3/8, or 1/8 times 3. So that ends kind of the 14.3 and 15.1, a little bit with permutations, combinations, and the fundamental counting principle, and then getting into a little bit of probability. So working on that homework, if you have any questions, please do not hesitate to email me or come see me. Would love to help you guys out on these.